In this video, we're going to be dividing polynomials in the hopes that it will help us factor some complicated polynomials. And then once we've factored it, we can find some more zeros. We're going to focus mainly on real zeros, although we'll hint at some imaginaries in some of these examples. We can use long division to divide polynomials, although we'll just start off that way, and then we'll use synthetic division to finish off the remaining examples. Synthetic division is a little neater, probably a lot faster, so we'll definitely use that method instead. But just to get an idea of why synthetic division is preferred, like let's do an example where we use long division and see why it's kind of a pain. So we're going to take this polynomial here, and we're going to try and divide it by a known zero. So that's going to be our first step today, is try and figure out what a known zero of a polynomial is. So we can graph this and take a look at the graph and see if we notice any x-intercepts that are easy to find the values of. In looking at the graph, we hopefully see that one of the x-intercepts crosses at 2, and so we'll end up using that factored form of that 0, x minus 2, to divide. And then we'll see what happens. When we divide polynomials, we just, in our first step, focus on the variable and ignore anything behind it, or we only focus on the initial leading term and ignore everything behind it if it gets more complicated than this. So just looking at x times what goes into 6x cubed. Well, hopefully you can think that 6x squared times x will give us 6x cubed. So now that we've figured out 6x squared up here, now we're going to involve that negative 2, and we're going to multiply what we have up top here by everything in this expression. And then we're going to subtract our values and start the process over again. So 6x squared times x is 6x cubed, and 6x squared times negative 2 is negative 12x squared. If we subtract both of those terms, we'll distribute our negative throughout. So distributing this makes it negative 6x cubed. If I combine those two terms in that column, I get 0. If I distribute my negative to the negative 12x squared, then that makes it positive. And so if I do negative 19x squared plus 12x squared, I get negative 7x squared. One more step, and then we'll repeat the whole process. Let's drop the next term down, so drop 16x. And now go back to playing the same game. How many times does x go into negative 7x squared? Or x times what is negative 7x squared? Hopefully you think negative 7x, because when I multiply that, I get negative 7x squared. That should be negative right there. Sorry, that's a little typo. And then negative 7x times negative 2 would be positive 14x. If I distribute my negative, there was a negative right there, so that makes it positive. Again, I get 0 in this column, but distributing the negative over to the 14x makes it negative, so 16x minus 14x gives me 2x. And we're going to repeat the whole process one more time. Let's drop this term down, and then ask ourselves, x times what is 2x? Hopefully you're thinking 2. Multiply your 2 times your x and get 2x, and your 2 times your negative 2 to get negative 4. If we subtract and distribute that negative, we have negative 2x, so making a 0 in that column. Negative times negative 4 is positive, so making a 0 in that column. That means we don't have any remaining values, or we have a 0 remainder, which is exactly what we want to happen if we are dividing polynomials by a known root. So because we knew that x minus 2 was a factor and that 2 was our x-intercept, when we divide that into our polynomial, we should always get a 0 remainder. If you use a root and you get a remainder value, well then something wrong happened in your division. Alright, so that's long division, kind of a mess. Let's see if we can do the exact same thing but use synthetic division and get the exact same answer. So we're still using the exact same polynomial up here, and we're still going to divide by 2. Here are a couple organizers that you can use to help you with synthetic division. But I'll walk you through the process, see if you can get the hang of it here. We know that 2 was our 0, so I'm going to put that in this spot right here. I like to put it in a little box. What we write off to the side of it are going to be the coefficients of our polynomial. So going back to the original one, we got 6, negative 19, positive 16, and negative 4. So we just list them next to each other. Let's draw a little bar here, and then we're going to start to fill in some values in these circled spots. First thing we're going to do is just drop that first coefficient all the way down to the bottom. Don't do anything with it, just drop it. And now we're going to do 2 steps. We're going to multiply our 0 by that number. So 2 times 6 is 12. We're going to put it in the next column. And then we're going to combine the values in our columns. Make sure that you're not subtracting, we're combining. So negative 19 and 12 together give us negative 7. Do the 2 steps again. Take your 0 and multiply it. So 2 times negative 7 is negative 14. And now combine the values in this column. So 16 and negative 14 gives a positive 2. One more time, 0 times that number is 4. And then combine the values in your columns and get that 0 remainder. That's what we want. So here's the trick with synthetic division. You're going to take these numbers on the bottom and you're going to put variables on them. And you're going to start with 1 degree less than what you started with in your original polynomial. So if we were dividing a cube, then our answer is going to start with our square, or exponent of 2. So these are the coefficients, and we just write them out and give them variables with exponents in descending order. So starting with 6x squared, minus 7, that's just going to be x to the first power, and then plus 2 is just going to be a constant without a variable, and we don't have a remainder there. So notice that we got the exact same thing, 6x squared minus 7x plus 2, in a much more concise and hopefully faster way than using long division there. So we're going to continue to use synthetic division for the rest of our examples. All right, so what could we do with that? So we took that, let's see if I'm in order here. There we go. Sorry, I'm skipping a page. We took that original polynomial. We used division to find a second factor, which ended up being a quadratic. So we have x minus 2, that was our original factor that we saw on the graph. And using division, we were able to get this quadratic factor out of it. Now, since we have a quadratic, we can keep factoring using quadratic patterns or quadratic formula to solve it, either way. And then we'll finally have a string of factors that we can get our real zeros from. So let's factor this quadratic here. Since we can't factor out any other common factors here, we got to find factors of our a times our c term that add up to our middle b term. So 6 times 2 is 12. What are factors of 12 that add up to negative 7? Hopefully you're thinking negative 3 and negative 4. So let's break up that middle term. Instead of negative 7x, we'll write negative 3x and negative 4x. And now we'll be able to use our grouping strategy. So taking those first 2 terms, what could we factor out? We could factor a 3x out, and that will leave behind 2x minus 1. Make sure you do a little check and distribute just to make sure that you get back to your beginning so you can be sure you factored correctly. So 3x times 2x is 6x squared, and 3x times negative 1 is negative 3x. So we factored that correctly. Take your last 2 terms and factor out a common factor. Seems like we could take out negative 2, which would leave behind 2x minus 1. Again, distribute. Negative 2 times 2x is negative 4x. Negative 2 times negative 1 is positive 2. Now we just got to put all our groups together. We got x minus 2, that's our first factor. We have 3x minus 2, there's a second factor. And then we have 2x minus 1 as our third factor. So we said we had 3 zeros. We saw 3 real zeros on our graph. And here are the values from our factor pairs. So what makes that 0 is positive 2. What makes this 0, just add 2 and divide by 3, we get 2/3. And what makes this last factor pair 0, add 1 and divide by 2, that's 1/2. So then we could go back to our graph, verify that those are our x-intercepts, and we were able to get them by using division to help us factor. Well, let's do another one. Let's go through that whole process again. 3 steps. First step is we need to find a 0 that we know is a root and that works so that we can use it to divide. So again, using the graph here, see if you can look and see an easy 0. Hopefully you can see that it's crossing the x-axis at 5. So we're going to use x minus 5 as a factor pair, but we're just going to use 5 as our 0 to help us divide. So setting up our synthetic division, use our coefficients here. We got 1 in front of x cubed. We got negative 4 in front of x squared and negative 25 to finish it off. Notice that we skipped our linear term, our x to the first power. We can't use synthetic division with missing terms, so we have to put a little placeholder in its spot. So we use a 0 anytime we're missing any terms in descending order there. So now we can play the game. Drop that first value down and then multiply with your 0. 5 times 1 is 5. Combine the values in your columns, get positive 1. 5 times 1 again is 5. Combine 0 and 5 gives 5. And then 5 times 5 in our last column is 25. Canceling that negative 25 and giving us a remainder of 0, which is what we want if we're using a root to divide. So now we have, instead of x cubed, we have x squared plus 1x plus 5. So there's our quadratic that we got from dividing. So here are our two factors so far, this polynomial being factored into these two things. All we have to do is factor this quadratic, and when we attempt to do so, hopefully you know that we can't factor it. There are no factors of 5 that add up to 1. So we have one real root, which I hope you saw when you graphed this. So where are the missing 2 roots? Well, they actually come from that factor form of that quadratic, but they're imaginary. So the way that you can figure out whether they're imaginary is to use the quadratic formula. In fact, you only really have to use what's called the discriminant, which is just the inside portion of our radical. If the value that we get from doing b squared minus 4ac is negative, well then that's how we're going to get our 2 imaginary zeros. So we could actually plug in our values and solve and get the values of those imaginary zeros, although that's not necessary for today. All we need to do is evaluate the discriminant, and that will tell us whether or not we have imaginary zeros, and we don't necessarily need the values quite yet. So again, if that discriminant, b squared minus 4ac, if that gives you a negative value, then you can't take the square root of a negative without involving imaginary numbers. So if it's negative, that tells you that you have imaginary zeros. If the discriminant, b squared minus 4ac equals 0, well then you can take the square root of 0, but you're just left with the answers of your fraction numbers in front. So you only have one real solution if your discriminant equals 0. And lastly, if that discriminant gives us a positive outcome, well, we can take the square root of it, and we can get 2 real zeros out of that. So that discriminant, you don't have to evaluate it, you just have to realize if you're getting positive values, a 0 value, or negative values, and they will tell you what type of zeros or x-intercepts you can get out of it. All right, let's practice that, and then we're going to add one more thing called the remainder theorem to it. It's just kind of a cool little trick. And then we're also going to see what happens if we try and divide by something that is not a root. So in this case, we just have this generic quotient here. Let's see what happens when we're trying to divide by x plus 1. We're going to take the opposite there. We're going to use negative 1 in our synthetic division here and write the coefficients for our polynomial, 1, 3, and 5. Drop that 1 down. Multiply negative 1 times 1, get negative 1, combine your column to get 2. Then multiply again, negative 1 times 2 is negative 2. Combine that column and we get 3. Now that's our remainder, the last value that we get. So how do we write this as a factor pair? Well, we get x minus 1, that was, sorry, x, where? Hold on a sec. Here's our quotient. We got x minus 1 and x plus 2. Where did those come from? So we got x here plus 2. There's that. And then the x, that should have been x plus 1 right there. That's what's confusing me. We were dividing by x plus 1, so x plus 1 should be there. We get x plus 2 from here. 1 less from our degree there, it means we start with a linear x term, so x plus 2. And then we write our division, or our remainder, as a divisor. So 3 over what we were dividing by, x plus 1. All of these things are being divided by x plus 1. We don't have to write it for these, but we do have to write it for the remainder. So this would be our final answer if we change that to x plus 1, x plus 2, and then 3 divided by x plus 1 is our remainder. If you multiply both sides by x plus 1, and that was x plus 1, then you could rewrite it like this, but no need to do that. The cool thing here, what happens with polynomials, is that when you have a remainder, that's actually the same thing as evaluating our function at that 0 value, if it were a zero value. So if I evaluate this function at -1, the outcome, or the output, is the remainder value. You can prove it by doing what we're used to, by just plugging it straight in. So squaring -1, adding 3 times -1, and adding 5, that also gives us 3. So why do we use division to evaluate a function? Well, we don't have to. It's just a cool trick. So that's called the remainder theorem. Now let's go back to my page that was out of order over here. All kinds of mess ups on this video, sorry. We're just going to do a few more examples here, just practicing all the things we just described. So we'll practice dividing and using that remainder theorem on this example. Taking this divisor of x minus 3 means we'll use +3 for a synthetic division. Writing our coefficients here, 1, -4, -17, and 6. We didn't miss any terms, so we're good there. Drop that 1 down and multiply. 3 times 1 is 3. Combine in that column, we get -1. -1 times 3, -3. Combine in that column, we get -20. And -20 times 3 is -60. Combine that in that column, we get -54. That's our last term. That's our remainder. So we can write that using 1 degree less here. So x squared minus x minus 20 minus 54 divided by x minus 3. So here's the answer to our quotient right here. This quotient became this. And then since we have that remainder, well, that means that if we had evaluated this polynomial at 3, the answer would have been -54. And you can check that if you'd like. All right, 2 more examples, just practicing what happens when we're missing some of the terms, when we're trying to use this synthetic division. So notice that in this polynomial 8x cubed minus 1, we're missing the square term and the linear term. So we're going to say 8 is our first coefficient, 0 for our x squared, 0 for our x to the first power, and then -1 for our constant. To use our divisor over here, we're going to take the opposite of what we see here, or what would make it 0. So we add 1 and divide by 2, so we're using 1/2. Drop that first term down, and then take half of 8, that's 4. Combine, we get 4, take half of that, that's 2. Combine, we get 2, half of that is 1. Combining gives us a 0 remainder, which must mean that there is a root or an x-intercept at x equals 1/2. So 2x minus 1 is a factor, and the results of our division is our other factor. So we have 1 less degree from a cube would mean 8x squared plus 4x plus 2. We know this was a real root. We can verify that on the graph, but we know it was because we had a 0 remainder when we divided. Checking this, hopefully you see on the graph that we don't have any more real roots, so this must give us our imaginary roots. We can check the discriminant just to make sure. Go ahead and do that. Do your b squared minus 4ac, and you'll see that you get a negative result, meaning that we have 2 imaginary roots there. And one more, doing the exact same thing. We get a similar result. We find that when we divide using what could potentially be our 0 or our opposite there of 3, we get a 0 remainder, meaning that in fact x equals 3 is an x-intercept or a root. Looking at the graph, though, we can see that there is only one real one. So our results here of x squared plus x plus 3 is going to give us 2 more imaginary roots. And again, you can check that discriminant or the graph to verify. So kind of a crazy method for factoring and finding your zeros of polynomial functions, but it's certainly a good tool we can use, especially when we have crazy looking long polynomials. We can use synthetic division. As long as we know a root, we can use that to keep factoring and find more roots. But as always, continue to look at the graphs and continue to look at other clues to tell you, like the discriminant, to tell you whether or not you have real zeros or imaginary ones. In later videos, later lessons, we'll get more into those imaginary solutions.